Good afternoon, everyone. My name's Tanya Hill, and I'm the astronomer for the Melbourne Planetarium. And here at the Melbourne Planetarium today, it's a pretty exciting day as we're launching a brand new planetarium show. It's called Capturing the Cosmos, and we've created it in partnership with a scientific organisation called CAASTRO. And I'm fortunate to have with me today two members from CAASTRO, Ben McKinley and Jack Line.
Hello.
They're both researchers at the University of Melbourne. And so what we'd like to do today is talk a little bit about the show, some of the Australian science that's happening right now, the telescopes that these guys are using to explore some of the really big mysteries and the big questions about the universe. So yeah, guys, do you want to just say a little bit about your research? Maybe Ben, what's the thing that excites you?
I work using data from a radio telescope that's located in Western Australia called the Murchison Widefield Array. And it's a new and innovative radio telescope that uses a lot of different antennas spread out right across the desert, and it's out there to be far away from any humans so that we don't get any stray radio signals coming into our telescope and messing up our images. And I use this data to try and peer back right to the very beginning of the universe before there was any stars and galaxies to look at. And so I'm just looking at hydrogen, which sounds really super boring, but there's a big gap in our knowledge and we don't know much about this hydrogen and what it was doing, so it can actually teach us a lot about how the universe formed and is evolving. So it's pretty interesting.
It really is. Astronomers get really excited.
We get excited about hydrogen.
This idea about hydrogen and about looking, because when we look up in space, we're looking back in time.
That's right.
It's taken light so long to reach us that we can see the history of the universe. And I know when I was talking to a lot of astronomers, they were all like, we want to go right back to see how the universe first began, see the first stars and galaxies that lit up, and really excited about this. And one way we used in the planetarium show to describe this excitement is, imagine if you had a photo album, a photo journal of your life, and you went back from what you did today and what you did the day before, but you get to a point where there's this missing gap where you have no idea. Maybe you've lost all your baby photos, or you don't know what happened in that period of your life. And that's kind of what these astronomers are doing, isn't it? Where we can map so much of the life of the universe except for this one little part, and we'd love to know what was happening right there. So Jack, what research are you doing?
So just like Ben, I work with the MWA, and like Ben says, we're looking at that period of time where there weren't actually any stars and they've just switched on. So that's about 13 billion years ago, and maybe even further. So just like Tanya was saying, it's a long time ago, and we're not really sure what happened at that time. And you can't really understand the entire universe until you've studied the whole universe. So that's kind of our idea.
Yeah, because that's CAASTRO, the organisation these astronomers work for. It's the ARC Centre of Excellence for All Sky Astrophysics. So it's about looking as much of the entire southern sky as possible to kind of piece things together. It's a little bit, I kind of describe it like we've been looking at the individual pieces of a jigsaw puzzle. We've looked at this galaxy that sits in this part of the sky, or this amazing star cluster over here. What these guys are doing is actually putting the whole jigsaw puzzle together and seeing how it all fits and all works. So sounds pretty right. Excellent. Well, if you've got questions, send them through. We'd love to hear from you. So we might start with one of the first questions from Keysborough College. And Jack, I'll hand it over to you. It was, what advances are being made with the wide field arrays, like the MWA in Western Australia that you work with? What advances are being made with telescopes like that compared to previous generations of telescopes?
Cool. So wide field means you can see a lot of the sky at the same time. Previously, we'd have telescopes that could only see small patches of sky. So as a kind of a scale view, the moon is half a degree across in the sky. We call that half a degree. The MWA, our telescope, can see around 60 widths of the moon. So if you think how big the moon is on the sky, we can see all of that at the same time. Now, to do that, you need special kinds of hardware. So I think an image has just popped up on your screen maybe, or is about to pop up, which is on. Awesome. So this is actually what the MWA is made of. It's kind of lots of little metal spiders, really. And we work in the radio regime. So Triple J, things like that, they're at the same kind of frequencies that we're actually trying to study this old fog of the universe. But due to the way these things are built, they can see such a large patch of sky at the same time. It means that we can look at the sky and map the entire southern hemisphere really quite quickly. We can basically make up a picture like within days of the entire sky. So the NWA has been surveying the sky for over a year now, and along with the same areas of sky as the SkyMapper project. But the advances that we're making is that we can see lots and lots of things at the same time. If you want to try and understand how certain galaxies behave, you need to check that they all behave in the same way, or kind of compare and contrast different types of galaxies. You can't do that unless you have hundreds upon thousands, sometimes up to millions of examples. So the real big advances in these wide-field telescopes is that you can make them super quick. That's it.
Yeah, no, that's amazing. And Ben was saying about the kinds of data that is pouring down from the sky all the time that these telescopes are gathering. Right. Do you want to? Yeah, you know the numbers.
Yeah, sure. Well, an optical telescope actually uses a camera, and you stick it on the end of the telescope, and then you can download an image straight to your laptop, or you could even look through it and see an image. Our telescope is a bit different, so it's got all these different elements, and for each pair of antennas, so one of those tiles that you see in front of you with the 16 spiders on it, that's one tile. So each pair of those generates a number for each, like depending on how often we sample it, but like many times a second. And so each time you get one of those numbers from each pair, and across a whole range of frequencies as well. So you multiply the number of pairs of antennas with how many times you sample it per second, with how many frequency channels you want to do, and you end up with this big number that ends up being like a terabyte of data for, what is it, a 2-minute observation? Or for every hour. Yeah, for an hour.
Wow.
So every hour we're generating an external hard drive full of data. So we have to pump that down a big fast internet link to a supercomputer and store it. And so all we basically have from our telescope is a whole bunch of ones and zeros. Just ones and zeros sitting there on the computer until an astronomer logs on and does some fancy magic with some software to actually turn it into an image. Because what we're trying to do by spreading out these antennas across the desert is to sort of mimic having one huge telescope. So what we have is one huge telescope that has a lot of holes in it. In fact, most of it is whole. There's not that much telescope. And so we have to do some fancy mathematics to actually turn those ones and zeros into images. And so that creates even more data, because you have the raw data, and then you have the calibrated data, and then you have images. And so we need big computers.
Yeah, so it really relies on computer power. I often talk about radio telescopes that, in some ways, as you said, there's a lot of hole in the data. It's kind of like you're looking through a picket fence, isn't it? And so what you want to see is what's beyond the picket fence, but you only see that between the little holes in the fences. But that's enough to then you piece it all together through the computers, and we get a really clear image of what radio waves are coming down from the sky. Actually, talking about radio waves, and in fact, we've got another picture of the same telescope, the MWA, but what we've done is we've changed the sky from being the normal sky to the radio sky, the signals that this telescope can detect. If anyone has been out and away from the city and has seen the Milky Way, that beautiful band of stars that crosses our sky, well, that bright line there in the middle of the image, that's how a radio telescope sees the Milky Way. Rather than it being nice and broad, we're not seeing stars, we're just seeing a very thin band of hot gas, of the gas that makes up our galaxy. And you might be able to just notice there's little dots that look like stars. Jack, do you want to explain what they're not really stars at all, are they?
Yeah, they're actually sort of big collections. So every single dot there is actually a galaxy. So a galaxy can have anywhere between 100 to a trillion stars, right? 100 billion to a trillion stars. Each of those is a radio loud galaxy. So most likely it has a black hole in the center.
We've got to love black holes.
Oh, black holes, they're the interesting one. But black holes, they're hungry. If there's gas around them, they sort of slowly eat this gas. As this gas heats, it gets energetic. And combine that with some magnetic field lines, you can produce lots and lots of radio waves, and they're super bright. So every single dot that you see in that image is a collection of between 100 billion and a trillion stars. So it kind of looks like our galaxy, which just has stars in it, but they are radio galaxies. And something else which is pretty cool, which is in the galactic center there, you can almost see sort of bubbles within that center. That's what we call a supernova remnant. Now, when really, really big stars get super old, they get to the end of their life, they actually end in this violent explosion, which we call a supernova, which you've probably heard of, which also SkyMapper, which we'll talk about later. It's good at finding those. But these supernova remnants, once you've had this big supernova, you have this big envelope of sort of material that gets thrown out, and it's kind of getting bigger and bigger and bigger as we go through the age of the galaxy. Each one of those bubbles is a supernova remnant. They're easier to see along the plane, so that's why we can see so many there. But you can make out 10s, 20 just with your eye, and that's an ancient blown-up star. Which they look pretty in optical, but they also look very nice in radio as well.
Yeah, they're amazing, these rings from the debris of a star that's exploded. So the supernova in the Milky Way, that's part of our own Milky Way galaxy, which, as Jack said, a few 100 billion of stars. And then our galaxy is just one galaxy amongst the millions of galaxies that are out there. And yeah, we can pick those galaxies up as little dots of light in the radio waves, which is pretty amazing. So the MWA looks at the sky in a completely different way to how our eyes do. But another telescope that CAASTRO astronomers work with and that we feature in our planetarium show is a telescope called SkyMapper. And it's more of a usual telescope, what people are used to seeing when you think of one. But it's doing something quite different as well, isn't it? It's in this wide field space, this looking at all the sky at once. Ben, do you want to explain a little bit about what makes SkyMapper a different kind of telescopes to other ones that we have?
Sure. So astronomers have, for a long time, focused on tiny little patches of sky, like if you can imagine holding a grain of rice up at arm's length and seeing just the bit of sky that's covered by that grain of rice, and zooming right in on that, and you can see thousands of galaxies and get amazing detail about.
So that's the Hubble Space Telescope.
Yeah,
if
like
you've seen amazing images from the Hubble Space Telescope, often it's only a small
and that's a teeny piece of the sky. So we know a lot about that little bit of the sky, but we know very little about the rest of the sky. Like, is that the same as the rest of the sky? Does the other parts of the sky look wildly different?
Yeah.
And what if we want to compare those galaxies to something like the MWA, where we've looked at this huge patch of sky? We only have optical telescope data from that little tiny patch. So what SkyMapper is doing is it's programmed in to automatically search the sky every night and map the entire sky, and it can do this relatively quickly because its field of view is much larger than that grain of rice. So it covers 30 square degrees.
So how did that Jack compare the MWA to the moon?
I think it's about, how many moons is that?
I think it's 10 moons across.
10 moons across. So
whereas the Hubble can't even picture the moon, can it?
No,
it's seeing like a tiny little crater on the
moon.
moon. Yeah, right.
And if you point the Hubble at the moon, it would burn everything and destroy it.
That's true as well. So, you don't want to do that.
So that's what SkyMapper is really good for. It can visit a large patch on the sky. It looks at it for a minute or so, and then it moves on to the next patch of sky, and the next one, next one. And what's also cool about it is it revisits the same areas again and again in order to fill up those patches of sky. And that allows us also to compare the images to see how they've actually changed in time. And that's one of the ways that we can find these things called supernova.
Yeah. So SkyMapper, and because that's the important thing, isn't it? Yeah, that it takes a view of the night sky and then another one again over and over. And we're used to not much changing. We don't see much changing in the sky with our eyes, but this telescope can pick up these changes too. Now, just hooked into, there's some great questions that are coming through, and one of them was, how many stars can we find now? And what's the number? And I don't know, I think all of us would have trouble actually giving you the number of stars. It's kind of like counting up the number of grains of sand on a beach. And I remember reading something on the internet about how they compared it, and it's pretty close. One of the things about astronomy, we're dealing with such big numbers. Getting things that precise is pretty hard. Would you agree?
I guess I would answer it by like, it depends. Like if you look up the sky, I think you can only see like a few thousand with the naked eye, and then if you look at that little rice grain in the sky with the Hubble telescope, you can see thousands of galaxies which each have billions of stars. So you're multiplying thousands by billions just for that rice grain, and then you've got the entire sky. So, I mean, to the human brain, there's an infinite number of stars. Like
yeah, it's pretty hard for us to describe. And someone's also asked, can you please tell me the earliest redshift interval at which galaxy and quasars are currently known to exist? So this is the idea. We're looking back, it's about 13 billion years ago, isn't it? They've asked for redshift. Do you guys know the exact redshift?
The current record of actually observed is something like 11, I think. We're somewhere around redshift 11. We think the first galaxies and stars formed somewhere around 16, 18, can't quite remember. We're not exactly sure, and that's exactly why the MWA works, right? The thing about astronomy, until very recently, is to do astronomy, you need light. I mean, that's kind of what it's actually based on. You need to look and see. Before the galaxies were there was nothing producing light. That's why it's so difficult for us to probe, and why we named that time the Dark Ages. It sounds a bit sinister, and it kind of is, because there was literally nothing producing light at that time. So we can't really see it until they switch on. And there's lots and lots of stuff in the way, this hydrogen gas.
Actually, we've got a picture of the fog of the early universe. So the idea is that it was mostly hydrogen gas, and it was light couldn't escape. Light couldn't get through and travel all the way to get to us until the first stars and galaxies started forming holes. It's kind of like they were burning away.
It's a Swiss cheese face, I like to call it.
Yeah, there you go. And that's something the MWA, it's one of the only very few telescopes in the world where it's about.
At the moment, yeah.
Yeah, the only telescope that can actually potentially try and find this Swiss cheese effect. It's actually looking for the holes in the fog to see how these first stars and galaxies lit up the universe.
And that's another reason we need wide field telescopes, because these patches, obviously this is almost a whole sky representation. You need to be able to see large patches of the sky to be able to pick up these kind of holes. And they only still exist on the imprint of the sky because of redshift and the expansion of the universe. So we're lucky that there's this snapshot in time and we can probe back, but we need really wide field instruments that also work at the right redshifts. So redshift and radio frequencies kind of go hand in hand. But yeah, I think 11 is the best we've seen so far.
And I guess,
pretty amazing.
Yeah, relating the MWA to that question as well. The beauty of it is the highest redshift ones have been found by looking at individual galaxies. We're not looking for the galaxies, we just infer that the galaxies are there because of these bubbles. So by looking at that large patch of sky, we can sort of figure out and use some detective work to figure out when the first galaxies formed, even though we can't even see them.
Yeah, it's amazing. And this is a great question from Penley and Essendon Grammar School. They're asking about how much will the data collected from the Square Kilometre Array, which is the next generation of radio telescopes, how much will that differ from the Murchison Widefield Array? Do you want to talk about that, Jack?
Fundamentally, it is actually the same. So an interferometer just means a collection of receivers, and you combine their signals in a specific way. The big difference is it's going to have lots and lots more, basically. In the Murchison Widefield Array, we have about 128 different receivers. In the Square Kilometre Array, there may be anywhere up to 1 million. And the amount of data that it produces just scales astronomically, unfortunately. One of the figures that got thrown around a while ago was the data rate transfer inside the Square Kilometre Array is going to be more than the global internet traffic.
So global, international, everything that's happening.
The entire internet, the amount of data that's flying around there
will just be in this telescope.
Will be in this one telescope. And then it's an astronomer's job to work out how to condense that into a way of actually, getting information from it. So we're in the regime where you can't store your data anymore. You have to process it. So you have to kind of do whatever maths you want to do to it on the fly. And that's kind of, at the moment, we're actually relying on a thing called Moore's law. So there's a law of computing that says as time goes on, computers get better. That's basically it in a nutshell. At the moment, the computers that we need for the SKA don't actually exist. We're just assuming that they'll get good. good enough to actually run this telescope. It's a good law, it's a fair assumption, but...
It's your job. You're going to be designing.
Yeah, exactly.
And building those computers.
Yeah, it's amazing.
Technology advancing, yeah, it's pretty incredible. So we've had another question from Penley and Essendon Grammar, and they want to know, why is it important to know about what's happening in the universe, and what do you think the impact is? Ben, do you want to, why is it that we should learn this?
Well, I think probably the best answer that I can think of for that is you just don't know what applications are going to come out of it. And for example, what we've discovered is, fairly recently, is we thought that gravity would be slowing down the universe. So we knew it was expanding and getting bigger and bigger, but because there's matter in it and things attract each other, it should be slowing down. So
because gravity should be pulling everything back.
So together. They had this idea, we'll use supernova and we'll measure how the universe is slowing down. And they measured it and they said, hang on, it's getting faster, it's getting bigger, faster. Why is that? Basically, they discovered anti-gravity. So there is a force, a repulsive force. And so, I mean, if someone can figure out how to actually make hoverboards out of that, it's going to benefit everybody in the entire universe.
Absolutely. So what you're talking about there is dark energy. Astronomers have given it this name. Mostly, I think it's dark because we don't know what it is. And actually, it links us back to SkyMapper, the telescope that we were talking about before. Because SkyMapper can pick up changes in the night sky, it can pick up supernovae, these stars that explode. And then it's by looking at supernovae are fantastic in terms of something called standard candles. Jack, do you want to explain what a standard candle is and why is supernovae so...
Yeah, so one of the issues that we face as astronomers is that the sky kind of almost looks like 2D to us, right? It just looks like a bunch of stars painted onto almost like a ceiling. But in reality, that's not true. We live in a three-dimensional universe that we can probe. So we have to try and work out how far away things actually are. And it's not as straightforward as you might think. And we have lots of little tools in our bag.
Because all we can do is see things, collect the light, isn't it? So we're trying to measure distance just by the light that these objects are giving us off.
So if you have something that you know exactly how bright it is, that's really useful. So imagine you have like a light bulb, you put it right in front of your face, looks really bright, put it really far away, looks pretty dim. You know that it's the same brightness though, it's just further away. So if you know exactly how bright your light bulb is and you put it on the other side of the room, you can do a calculation comparing how bright it looks to how bright you actually know it is, and then you know exactly how far away it is. There's a certain type of supernovae which we know exactly how bright it is. So if you can watch them going off and you can associate them with a galaxy, you know exactly how far away that galaxy is. The duality of the awesome thing about redshift is it means we can see things in the past, but it also changes the frequency that we see them at. So we need to know how far away something is to know exactly what's happening in it. So standard rules are essential. And things like SkyMapper are able to see them all the way across the sky, which is very, very useful.
Yeah, so it can find these supernovae. They're called Type 1a supernovae, not the most original of names. But this cool thing about these supernovae is that it's not just a star that reaches the end of its life and explodes. It's a star that is actually orbiting around another one, and it's funneling gas off that second star until it just gets too heavy, can't cope anymore, and pretty much implodes. It's an implosion that causes the supernovae. So we know how bright that supernova event should be, and as we said, that's our standard. The dimmer it appears, then we can get to measure distance, and that's where things are much further away than we thought. So the universe, rather than just getting this kick at the Big Bang and expanding, for some reason dark energy switched on and is pushing everything even further apart. Now I've got a great question here. I'm not sure which school it's from, but what is the universe expanding into? Ben, do you want to try and help out? It's a bit of a misnomer about it.
Yeah, sure.
How do we talk about the universe expanding?
Yeah, it's not something that our human brain can really picture or comprehend, because you're talking about sort of an extra dimension of space that you're not aware of. So it's not the universe expanding into anything. There wasn't like an empty universe with a little seed that got bigger and bigger and bigger. It's the universe itself, like it's the space that we're moving through is getting bigger, which is kind of mind-blowing. You don't notice things so much because there's other forces that are holding things together here on Earth, like this table and me. But the space around us is getting bigger, but it's kind of, it's not an effect you can really notice until you look at things that are really, really far away. So the amount of stretching is proportional to how far two things are apart. So that's why we need to look at these really, really bright supernovae that are really far away to see how the universe is actually expanding. So it's space itself, so it's not expanding into anything. There is no middle. Everything around us is just getting bigger.
Yeah, and so it's one of these things, Big Bang was the start of the universe, and in some ways that Big Bang is all around us,
That's
isn't
right.
it, even right now?
Yeah.
Because it happened everywhere in the universe, and so it happened right where we are as well. It's one of these crazy ideas. And so the universe is expanding. Dark energy tells us that expansion is getting faster and faster. Jack, what do you think is going to happen in billions and billions of years into the future?
Well, if it goes the way that it is, everything's just kind of going to get a bit cold, and it's all going to turn into a rather boring universe, unfortunately. We're going to kind of have a big freeze, and the temperature will just slowly go towards absolute zero. Lots of interesting stuff will happen in between. There'll still be lots of stars blowing up and radio galaxies switching on and turning off. But yeah, at the moment we think it's going to be pretty boring at the end of everything.
So it'll even get to the point, isn't it, that so at the moment, on sort of small scales, which even I'm talking about the size of a galaxy, gravity is able to hold the galaxy together, and so it's not expanding against dark energy as yet. It's kind of the distance between galaxies that's expanding. But eventually we could get to a point where dark energy can overcome the forces of a galaxy holding together. You know, we would lose the stars in the night sky, I'm guessing. Would it get to that point that the stars would be moved away and you know, our sun would be all alone, and eventually...
Well, we might run out of hydrogen eventually, right? So there wouldn't be any fuel left.
Nothing more to make stars.
So gravity is strong enough to hold our little island galaxy together. So, and I think the local galaxies that are orbiting around, they're pretty much bound. So I think the stars would probably stay until they all burn out and disappear. But the MWA image that we saw would completely change. So that will fade away and it will be blank.
Right.
And future MWA astronomers will just be staring at nothing. It'll make the surveys a lot easier.
Slightly
in the future. So get into astronomy now because it's all going away from
But and again, of course, we're talking, you know, astronomers talk about time in billions of years. So, you know, it's well, who knows how humanity and things may have evolved by then. So let's see, what other questions do we have there? So one of them sounds quite interesting. If there's so much missing mass, why is the expansion of the universe still accelerating?
You want to tell us? Yeah, we're not entirely sure. The reason we call it dark energy is because we can't see it and we don't really know where it comes from. And similar with dark matter is the fact that we can't see it. They're kind of holes in our current theory. It can be slightly embarrassing as an astronomer to admit that, about 70% of the universe, of the energy budget of the universe is dark energy.
Which we don't know.
We just shrug, right? You can't know everything straight away. We have to put in effort and work it out. But that is one of the big questions. I don't know. No one does, I think.
Yeah. And I suppose actually going back to that early question about impact as well. I mean, what was it, almost 100 years ago when quantum mechanics was discovered. And so this is talking about the physics of how things work on a really tiny scale, on the scale of an atom. And there's all these strange probability effects. And at the time, the scientists were going, look, it's interesting, it tells us something about our universe, but whether it's ever useful. And now every device we use, all our computers, iPads, all the rest, they're built, they're made to be so miniature because of quantum mechanics. So I often like to think, you know, at the moment, on the other scale, in terms of the big scale of the universe, we've got this dark energy, 70% of the universe we don't know. Who knows what advances that may lead to.
Yeah, that is cool.
It's a really interesting field. Okay, we've got a couple of questions coming in on my favourite topic, the topic of black holes. Jack, do you want to explain what would happen if you got a bit too close to a black hole?
Spaghettification. So gravity is basically set up by how much stuff you have, right? And in a black hole, you have a lot of stuff in a very, very tiny point. So you get this really intense gravitational field. And gravity you feel the force of gravity more the closer you are. But it also has this very strange effect of changing the way time works. So at the edge of a black hole, you have crazy things happening where gravity is getting stronger the closer you get to it, and also time is kind of slowing down. So essentially you can kind of almost see your feet going off, because they're kind of getting pulled off anyway and sheared off, but the time that the light takes to get to your head changes as well. So you get spaghettification, pretty much.
So stretched out into a long, thin piece. Because even over, gravity changes on Earth too. Gravity at the surface of the Earth is much stronger than you go into space, 100 kilometres up. But over the distance of how tall we are, the gravity change is pretty minimal. But you get close to a black hole, and the gravity change between your feet and your head is enormous, and that's what stretches you out. And I love the whole time dilation idea, the fact that, and it is time for you actually, you feel time the same way, but it all slows down. So you can look back and actually kind of see the universe speeding up in a way, seeing, because the universe is ticking away at its normal rate, so time out there seems to go faster.
And it isn't actually fully theoretical. We have proven these things. If you put a clock on the surface of the Earth, a very, very accurate clock, not just your stopwatch, but if you put a very accurate clock on the surface and stick it up on a space station, just the fact that you're orbiting around the Earth means that time changes, or the passage of time changes slightly for the clock on the ship. And we've done this. We've seen that there is a slight difference in the time measured up in space versus on the Earth. So I know we throw it around, it sounds like science fiction, but it's just science. Yeah. And it's actually true.
It's another thing we use every day. If you've ever used GPS to get somewhere, you're talking to a satellite which relies on a very, very accurate clock, and its clock is ticking, what can I remember, it's in the order of microseconds, different to how the clock's here on Earth. But that would translate to, if you didn't take that time difference into account, then you would start to be like a metre away from where you wanted to go, and then a kilometre, and then it would just get worse all the time. Yeah. So
they calculated what that time difference is, and then they set the clocks differently on Earth, and then they send them up so they're exactly synchronised.
Yeah. Cool. So we're using relativity and time dilation all the time.
Yeah. And Einstein never got to see this.
So someone wanted to ask a really good, I think it was from Gympie High School, about if black holes are sucking material in, like we say, turning things to spaghetti, and they're black, that's why they were named that way, how do we see them? We just put up a radio image of all those little dots and said you're looking at sort of black holes, at galaxies powered by black holes. Why is it that we can see a black hole?
Okay, well, there's an exciting new way that we can actually see black holes directly, which we can talk about.
Let's do the normal way first.
But the normal way first is we're not actually seeing the black hole. So we're seeing the stuff around the black hole. So what happens, because the gravity is so strong around a black hole, and as Jack said, they're really hungry, things are going into them. But it's actually really hard to fall into a black hole. So things start going really, really fast and getting torn apart, and it's really violent, and you end up with these big jets of energy that are shooting out either side of the black hole. And so that's the bit we're actually seeing. It's what we see from the radio telescope is the radiation caused by little particles, electrons, that are whizzing around very, very close to the speed of light and through a magnetic field. So they're whizzing around out of these jets, and that's what we see.
Yeah. So the radio telescope sees the jets. They're kind of spewing out. I don't know if anyone does it these days, but there is a Vitabrits or something or other. They're always the biscuits, and if you squish them together, all the butter and the Vegemite can come out through the holes. It's kind of like that, the jets of the Milky Way. So that's what a radio telescope sees. An X-ray telescope, they see all the material as it's spiralling down and going round and round, slowly trickling into the black hole. It heats up due to friction, just like rubbing your hands together, and it gets so hot, millions of degrees, that the gas actually shines at X-ray wavelengths, and so that's another way we see them. But very recently, just last month, we found a new way of looking for black holes and what happens when two black holes actually circle around each other and eventually collide to form a single black hole. I'm talking about the amazing discovery of gravitational waves. So, Jack, you're nodding there. Do you want to explain what is it?
So this is some extreme physics. When you have two black holes, and they start kind of doing this one leg down, so they're about to collide and die. They kind of do like a whirlpool going down the plug hole thing where they orbit each other very, very quickly. Now, because they have so much mass, and we said that mass affects gravity, there's huge gravitational effects. And it turns out that gravitational effects actually change the shape of space. So you actually stretch it and warp it. Because you're going in this regular pattern, the way that these two black holes kind of orbit each other, they warp space in a pattern, in a systematic way. Essentially, you can almost think of it as just doing this, really.
And this way as well. It's kind of, you can
squeeze
and pull, don't you? Yeah.
So kind of, if I was at one end of the laser and Ben was at the other end of the laser, I'd start doing this and you do that, right? Yeah. You go away, I come in, go away. So what we can do with these instruments that we set up is you can look at space stretching. We know how long light should take to go a certain distance, and lasers use light. So if you can shoot a laser from one point to the other and watch how time changes, how long it takes that laser to get from one point to the other, and you watch it changing in a rhythmic pattern, the only thing that can cause that are things like binary mergers, things like black holes going around each other. So you can actually watch space warp and change shape. And Einstein predicted these things. They're called gravities, gravitational waves. We've only just got to the point where the optics, the lasers and the mirrors that we use have got good enough to actually see these changes, but they're minuscule, right?
Like the size of a proton, smaller than a proton?
Yeah, I think it's smaller than a proton. So things inside the atoms, which are what make us up, you have to be able to look at space changing. Well, I mean, obviously doing this, that's a little bit bigger than the size of a proton. So ridiculous accuracy, but they've actually done it, man.
Yeah, which is pretty amazing. So what's happened? The way Einstein kind of has taught us to think about the universe is this idea that there's this sort of fabric of space-time. It doesn't really exist, but it's a nice analogy to be able to think about it. And often the way it's mentioned is that space-time is like a trampoline. And so gravity is just you put a big bowling ball on your trampoline, it's going to create a big hole in the centre, and that's what gravity is. But then, of course, if you bounce and pat the trampoline, then it's going to send ripples through as well. And so these are what the gravitational waves are. They're the ripples that travel through this fabric of space-time when these big, massive objects are moving around. And it was, someone remember the two black holes that collided? It was 1.3 billion light years away. So this happened 1.3 billion years ago, set off these ripples, just like you'd throw a rock into a pond, set off some ripples, and the ripples are going to be dying down, and yet we've still managed 1.3 billion years later to be able to detect this kind of dying down of the ripples as it's passed over the Earth and made the Earth kind of squeezed and stretched by this minuscule amount. Yeah. Absolutely amazing. So, astronomers, scientists around the world are really excited about gravitational waves. What more can they tell us? Why is this so exciting?
The amazing thing about it is it's a completely new way of doing astronomy. It's not like a different frequency of light. It's not light. It's a entirely new scientific field. These gravitational waves, as Tanya said, it's so weak and small, you can only detect them from things that are absolutely catastrophic, so the most violent things, like these two black holes merging together and getting so close and then actually smashing together. And do you know how to do the sound of what that sounded like? If you could, because what's interesting is this actually, like the two black holes smashing together, if you could, it's in the audio range, like if you could actually hear this with your ear, which you can't, but if you could, it'd sound like whoop. It's like, it makes a really weird sound. So, and that's happening all the time throughout the universe. So like, eventually when we get even bigger ones of these interferometers that are much more sensitive, we'll be able to look at the entire sky and see whoop, 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 and all these black holes smashing together. And I think the holy grail of it is actually looking right back to the Big Bang itself and trying to measure the gravity waves from when the actual birth of the universe, like actually looking at and sort of listening to the birth of the universe itself. So who knows what amazing physics we'll be able to learn.
Yeah, because that's something that light can't probe.
That's right. It's
impossible. We were
Mm.
talking about the MWAs looking for these holes in the hydrogen fog where the first stars and galaxies lit up. But we go further back, and there's this radiation we call the cosmic microwave background radiation. It's the remnant of the Big Bang. And it allows us to see just 380,000 years after the Big Bang. So the Big Bang happened, 380,000 years later, we've got our first picture of light. But we can't use light to probe that first instance, but gravity waves we can, can't we? So, eventually as the technology gets better and we're able to detect more of these gravitational waves, we can probe right back to the earliest times, which will be really very exciting. So gravitational waves is a new way of looking at the sky. We talked about light and radio with our telescopes. Pex has asked us what other forms of electromagnetic radiation are out there.
Oh, all kinds of fun stuff. Anything under the sun. So UV, which you're supposed to avoid with your sun lotion, that's out there. Infrared, we use to look at dust. It doesn't sound interesting, but dust is actually very important in the way that light signals reach us. You've got X-rays, as Tanya talked before. Gamma rays, so there are these things called gamma ray bursts that go off every now and again. Again, they're very energetic. So gamma rays are the most energetic light that we can see. And they are pretty cataclysmic events. And then microwaves, so they're, we use microwaves as well. There's an interesting new development in radio waves which are called FRBs, which are fast radio bursts. It turns out you can mimic the signal of these FRBs by opening your microwave oven right next to your instrument, which we just recently had problems with at the Parkes telescope. It's quite a funny, interesting bit of science, but there's an actual paper on don't open your microwave next to your radio telescope.
So the key is it's the microwave if you're too fast to want your food. If you use the microwave and you wait the full minute and then you get your food, you're okay. But if you decide after 50 seconds, I'm hungry now, I want it, and you open, then there's enough microwave energy, isn't there, that sets out, and the telescope thinks that it's one of these fast radio bursts.
Yeah. So
a different thing that astronomers are seeing in the night sky. But all the different kinds of, and they're all different kinds of light, it's just their frequency changes or their wavelength changes across. And each of them tells us something new and different, doesn't it? So you were saying about the infrared with dust. One of the great things with that is, firstly, there is a lot of dust out there in the universe, and so things are hidden behind the dust, and we can use infrared to kind of see some hidden things. Can't we? Can look into star-forming regions. Ben, do you want to talk about that at all?
I don't know a lot about the infrared. I do know that one of the tricky things about infrared is that it can't actually penetrate our atmosphere very well because it hits the water molecules and it basically gets blocked. So in order to see this different view of the universe where you can peer at and look at the dust and the warming that's happening, you have to get away from the atmosphere. So they either stick it on a satellite, one of these telescopes, or a cool thing that they actually mounted a telescope inside a Boeing 747 and they fly it up above most of the atmosphere, and that's called the Stratospheric Observatory for Infrared Astronomy, and it's one of the reasons why I called my daughter Sophia with an F.
Oh, okay, because the observatory, that's fantastic. Yeah, no, that's great. So so we have all the different types. Ultraviolet light that you were talking about, that allows us to see some of really young stars, doesn't it? When stars first are born, they're very energetic in ultraviolet light, so you can kind of use all the different wavelengths of light, and again, I think it's something that CAASTRO does really well in terms of it's not just looking at all the sky, but then it's all the wavelengths as well, isn't it? To really piece together what's going on out there. So a last question I think we might have. We're going to bring it all the way right back to home, back to our little solar system. So our sun, which is just one of the many millions of stars in our galaxy with all its planets around it. And back in the 70s, the Voyager spacecraft was launched off Earth and has gone out to probe the solar system. And the question is, has it left the solar system? Jack, have you been following Voyager at all?
Technically it has. So
there's different kind of edges to the solar system though, isn't there? So go for it.
So It is still sending us data, which is an
amazing.
absolute testament to the instrument. That's insane. Like, it's
What
been
would be
going
the computer power on Voyager? Wouldn't it be a watch?
maybe
would it?
like less than a Casio calculator that you can get these days.
Yeah.
I mean, that's what they send people to the moon.
And that was amazing. Yeah,
Yeah.
that was amazing at the time.
So it can basically sample how many particles it's surrounded by, right? So we know that our solar system is traveling through our galaxy, and you have what we call a bow shock at the front. So essentially there's a bunch of particles and matter associated with our solar system, and then there are things that aren't bound to it, they're sort of outside it. And it's almost like we're a ship sailing through some water. You can look at the way the water flies off the front of the hull. So there's a big rise in the density at that point. And then after that, it's there's nothing, right? And Voyager, it suggests from the data, the way that the density has changed, how much stuff it can see, that it has pierced through that. It's gone outside. So it looks like Voyager is out on the solar system, which is the only thing that has ever done that. Universally, tiny scale, but on human scale, massive.
Yeah,
Really
it's
interesting.
pretty amazing that we were able to do that. So look, I want to thank both Ben and Jack for being here today. They're both researchers at the University of Melbourne and part of CAASTRO, the ARC Centre of Excellence for All Sky Astrophysics. And as I said at the start of this, one of the reasons that we were doing this today, and it's a big day for the here at the Melbourne Planetarium at ScienceWorks, is that we're launching a brand new planetarium show called Capturing the Cosmos. It tells you all about the MWA that we've just talked about, which these guys work with, and also the SkyMapper telescope as well, and what they're doing to probe dark energy, to probe the cosmic dark ages, these big mysteries that we're trying to solve. We're trying to understand more about the universe. So thank you all for your fantastic questions, and maybe we'll chat again soon sometime. Thanks.
Thanks, everyone.